think you all agree with me that this equation has three signs, right? This is Hamiltonian, wave function, and energy or property. So the Hamiltonian will determine what physics you are looking at. And the wave function describes the probability distribution of particles, in our case, electrons. And then the physical observables is functionals of Hamiltonian wave function. So the first thing is that all electronic structure calculations, you have to start with a certain Hamiltonian, depending on what physics you are looking at. So today I would like to tell you that we have constructed the complete and continuous Hamiltonian ladder. And the right arm is due to my group, and the left arm is coming from the literature. So let me explain to you a little bit. First of all, we can split the whole ladder into three parts according to spin symmetry and charge conjugation symmetry. So if you know in the beginning that the spin-orbit coupling is negligible, so then you consider a spin-free calculation. Here we have exact Y component theory, which cover scalar relativity to infinite order, as computationally exactly the same as a well-known Schrödinger Coulomb equation. So in my opinion, that nowadays we only need to concern this exact Y component theory to replace this Schrödinger equation, because we get infinite order scalar relativity for free. Okay, so if spin-off coupling become important, but can be treated as perturbation, so we have this kind of new equation. But if spin-off coupling is very strong and has to be treated very rationally, we have both quasi 4 component and exact 2 component. Both equations are computationally exactly accurate, have exactly same accuracy as Dirac-Coulomb-Bright equation, but computationally much simpler. So up to this level, we are assuming that the electron-positron pair correlation and annihilation effect are negligible. And this is usually the case that for material science, for chemistry, low energy physics. But if you are really interested in ultra high precision spectroscopy, you have to consider so-called QED effect, including electron-positron pair correlation, annihilation effect, retardation effect, and so on. The QED, QED is the highest level of theory for electromagnetic interaction between charged particles. However, QED is computation too expensive. And nowadays, the QED can only be applied to at most 3 electron single ions, this kind of system. So it's not chemistry, not material science at all. So to resolve this issue, we proposed what we call effective QED theory, which can readily be applied to many electron systems. So let me show you one results. So if you follow Feynman's QED formulation, okay, for second order energy, you already need 28 Feynman diagrams. So each diagram may contain some unphysical ingredients, such as surface interaction, divergence, and so on and so forth. And high order, there are too many high order diagrams. You cannot easily go to high order diagrams. The problem is that the more electrons, the more diagrams. That's exactly why QED cannot be applied to many electron systems. So according to my formulation, up for the same signal of energy, I only have 3 diagrams. And these 3 diagrams are really standard many body theory, these lowest order diagrams. So I can easily go to high order terms. Basically, I want to say that every Hamiltonian determines an equation. So in the end of the day, you should select correct Hamiltonian according to your target physics, especially the accuracy. So physics and accuracy determine which Hamiltonian you got to pick up from this ladder. So this is my most recent review paper on relativistic theory. It was published just 2 weeks ago. So basically, you find everything on relativistic Hamiltonian from this review. Or if you want to learn more, you can, we have this book. This is the most recent book on relativistic quantum mechanics. Okay, So of course, after you decided to which Hamiltonian you take, so you want to solve the Hamiltonian, solve the equation. The first thing that you have to design, to know how to design or contract many electron wave function. That's exactly electron correlation or many-body effect. So correlation or many-body effect is really embodied in the wave function. So let me tell you one example. So everybody knows the hydrogen molecule, right? So you know this is the diffusion energy curve, a potential energy curve of H2 molecule. You see nearby the equilibrium distance, the simplest theory, the one determined wave function theory, just Hartree-Fock, works very well. But if you let us stretch two hydrogen atoms away and away, then the one determinant wave function theory really breaks down. Really breaks down. I think compared to the exact theory. You know why? As it's a simple, the reason is very simple actually. Nearby the equilibrium distance, you have this bonding and anti-bonding. There's a very large gap. So the two electrons occupy the sigma G bond, and this give you a one determinant. So this is a very, very good approximation. But when you stretch the H2 molecule, there's a bond, the bonding and anti-bonding orbital become nearly degenerate. As in the decision limit, you have exactly the same two hydrogen atoms. So these two orbitals are exactly degenerate. So conventionally, that we call the correlation between the nearly degenerate orbitals is called a static correlation. And then the correlation from these higher lying virtual orbitals, and they call it dynamic correlation. So in short, conventionally, we try to decompose the overall electron correlation into static correlation, which is due to near degeneracy, and a dynamic correlation, which is due to the appearance of enormous number of virtual states. Okay, we have static correlation and dynamic correlation. Then, of course, we can classify our chemical systems into four families. So if your system has no dynamic static correlation, no dynamic correlation, this kind of Hartree-Fock, the single determinant function is essentially exact. And of course, lucky system, right? This is the simplest system. On the other hand, if your system has no static correlation, but only dynamic correlation, that means in this case, you have big homological gap. Then this functional theory, more precise signal order perturbation theory, couple cluster theory works perfect. Another extreme case is that your system has no dynamic correlation. That means all the orbitals are nearly degenerate. So for this particular case, it's called density matrix renormalization group theory is one of the best options. But our daily life chemical systems, like in chemistry, material science, solid state physics, your system have both static and dynamic correlation. Okay, this is a challenge. So then we also can classify our methods into two families. One family is a single reference. That means that no matter how many nearly degenerate states you are facing, but you still can start with a single reference, single determinant, but go to higher level excitation. Okay, so in material science, people often use what's called GW method. Okay, this belongs to this family. Okay, so but more effectively, that you can go to the multi-reference. Since for in this particular case, since you know two determinants strongly couple each other, so naturally you want to treat these two determinants mathematically on equal footing. Then this remaining spectrum of treated at the lower level, and this is called multi-reference approach. And this is most popular in quantum chemistry. Okay. Then of course what's the multi-reference things? So multi-reference is you start with certain number of nearly degenerate, let's say determinants, and then you diagonalize your Hamiltonian. Okay, diagonalize the zero sort of function. And this part you already described called static correlation, because this static correlation described as nearly degenerate configurations. Then the remaining part of the wave function, the exact wave function, is a zero sort of wave function plus additional things, and this is called dynamic correlation. So this is a general rule for it's called multi-reference approach, including multi-reference perturbation theory, couple cluster, or configuration interaction. All of these three families of methods belong to this similar philosophy. Then of course we can classify all the family of methods into three classes. When the first treat static, then dynamic correlation. This case that the zeroth order functions with static correlation, but they are used to contract dynamic correlation, but are fixed. It's obvious that dynamic correlation do not see static correlation because the coefficients are fixed. The opposite way is that you treat first dynamic correlation followed up by static correlation. That means the zeroth order coefficients are not used to contract dynamic correlation at all. So there are solution many methods. Of course, obviously that the demerits of such method is that dynamic correlation does not see static correlation because this static correlation is not used to contract dynamic correlation. The third family of method, of course, try to treat static and dynamic correlation on a more balanced level. That means zeroth order coefficients are used to contract dynamic correlation correction, but relaxed in the end. So there are also, again, many methods, but it's also a problem in this kind of family of methods. So here I have introduced the numbers. NP is the number of solutions you want, number of states you want. So in this set of method, people usually diagonalize a huge, very large matrix, 10 to 6, 10 to 9th power, this kind of order of magnitude matrix to get just, let's say, one state correct. NP equals 1, and one state correct. So you're obvious that you still have a lot of redundant information there. So to resolve this issue, a few years back, with my collaboration, we introduced what we call restricted static dynamic static SDS framework. That means no matter how many orbitals and how many electrons you want to correlate, we always diagonalize 3NP by 3NP matrix. NP is the number of states you want. So if NP is equals 1, you diagonalize 3 by 3 matrix to get 1 state correct. You diagonalize 6 by 6 matrix, you get 2 states correct. So this is we call general, let's say, a scenario to design new wave function. So let me explain a little bit how this idea came to me actually. Suppose now you have the exact spectrum of your quantum mechanical equation. So formally, we always can classify the whole spectrum into, let's say, NP primary state, NS secondary state, and NQ external state. These are formal things, right? The specific number of specific numbers, of course, depends on the situation. For example, if NP equals 1, there's only one state which is very below all of the other states. And this certainly is called weakly correlated system. Okay. So another extreme is that NP equals 1, that includes the whole spectrum. That means all of the states are nearly generate. So this is typically happening in the thermodynamic limit. You have an infinite number of particles or electrons in your case, okay? But typically, let's say, for materials or chemistry or physics, so we have a number of states. NP maybe as 10, 100, or 1,000, but NP usually much, much smaller than the whole dimension, okay? That's the situation we want to handle. So of course, this is a so-called a feature, general feature of the exact spectrum. The major question is that how do you contract so-called NH1B set to mimic this feature? It's obvious that individual determinants do not have this feature. Only combinations or linear combination of determinants, which we call contract functions, they can likely have this spectrum. Okay, so then the simplest answer is that you pick up NP functions from this subspace, NP function from this subspace, and NQ function from this subspace. Then you have this exactly what I call 3NP answers. So you have a NP zeroth order functions. So you have for static correlation, you have an NP first order function for dynamic correlation. Then you can introduce another NP state which describe the change of static correlation in the presence of dynamic correlation. That's why I call it static, dynamic, again static. So the 3NP structure. So you diagonalize 3NP by 3NP matrix, and that's it. We call this SDSCI. This is a really minimal multi-reference configuration interaction approach. Now, this approach, you diagonalize for NP equals 1, you diagonalize 3 by 3 matrix. NP equals 2, diagonalize 6 by 6 matrix. That's very simple enough. But however, this method is still scale as 6 power for number of electrons. So we can make it even simpler. So that we replace the most expensive block. That means the interaction between function of this subspace. Okay. So replace it with 0th order Hamiltonian. Then the scaling will be reduced by 1 order. So in the 5th power of the number of electrons. And this is the lowest scaling of all post-Hartree-Fock wave function-based correlation method. So this is the cheapest method. So let me give you one example to show the performance of SDSCI and SDSPT2. This is spin state splitting of ferrocene. Okay, so ferrocene, you have several spin states. So in this particular case, we have no experiment to compare only number. We can compare this multi-reference CI as a benchmark. And you can see that the CASP-P2 and NEP-P2 are the two most popular variants of multi-reference perturbation theory, but they really predict these two states, triplet B2, quintuple A1 state, and near degenerate. You see, 40, 40, and 35, 30, near degenerate. However, if you look at the benchmark result, they are separated by 8 kcal per mole. And this energetic separation is very reproduced by our approach SCSP2. Okay, NEP even predicts the lowest state. This state actually energetically very high, but it predicts lower than the Golan state. Okay, so another thing that our approach treats single and multiple states in exactly the same way. So I think our approach somehow beat these popular approaches. Actually, this is not the end of our theory. Actually, since we diagonalize matrix, we get new vectors, right? New trivectors, and from a new trivector, we can do additional dynamic correlation and static correlation. Again, this is called iterative configuration interaction, and this iteration procedure. So let me show you one simple example just to prove the concept. And this is a water molecule, like a double stretched water molecule. Look at the red curve, a double stretched water molecule. Okay, there you have two near degenerate configurations. The Hartree-Fock is very, very bad. It's the energy is very, very high. But we can do the iteration and continue monotonically convert to the exact solution. Okay, if you have a better starter up, you have 4 electrons in 4 orbitals, then of course it takes only 5 iterations to reproduce the exact solution. So in this case, we have 10 to 8 determinants. This is not a trivial, not a small problem at all, actually. So anyway, so again, this is a proof of concept. So iterative configuration interaction, or ICI, is really can really reproduce the exact solution. Okay. Another very nice feature of ICI is that each iteration actually has a physical meaning. You really can reproduce the standard results by standard methods. So I have no time to explain in all detail to you, but you trust me that each iteration of ICI has a physical meaning. That means when you do the calculation, you can stop somewhere or anywhere, depends on the accuracy you want to really target. Okay, this is a nice point. Of course, ICI is exact, but expensive. So now we want to let's say improve the efficiency of ICI. That means combine with selection. You know that the number of determinants is a really huge number, but essentially a majority of them do not contribute to the energy. So the main problem is that how do you get rid of these important configurations such that you pick up the important contributions in the early stage? Okay, this is the essential question. Okay, so if you look at the structure of the Hamiltonian matrix, you say some block may be very large. Some block, even half of the block, let's say, is important. The remaining part is near zero, and some blocks are near exactly zero. Some blocks are near zero. So that is the structure I'm talking about. The Hamiltonian matrix has this very sparse matrix structure. The question is, how do you make use of this structure, right? A priori. So we figure out what we call a tabulated orbital configuration based unitary group approach. Okay, I think it was published last month. So we have some ideas related to pre-splitting the configuration pairs, and we can select individual configuration state functions, and we can reuse this unitary group coupling coefficient. We can split the Q function into subspaces to reduce memory requirement. So in the end, we have only a single parameter to control the accuracy. So we have exact spin symmetry no matter how you do the selection. Okay, so we can describe both ground and excited states, especially highline state like co-excitation. Okay, like co-excitation, we can target highline states without touching low-lying states. And this is, I think, very amazing method. Let me again show you a showcase. This is benzene molecule. Okay, benzene, of course, is not really strongly correlated systems, but we have 30 electrons, 108 orbitals, and this is you will generate 10 to 33 power configuration state functions, or 10 to 34th power number of determinants. That means if you do exactly, you have to diagonalize the matrix of this size. Okay, so nobody can do this. Okay, nobody can do this. So now we follow a selection procedure. So we have, as I said, we have a single parameter to control the growth of our wave function. So we can, of course, test different values. Let's say if we get these points, then of course we can, in the end, the largest calculation here. So we selected 1 million configurations, and the remaining part, 10 to 12 powers, is cut out by perturbation theory. That means we cut down this size of problem down to this. Okay, so 10 to 20th power is gone. Right. So now you see, in this regime, you have a lot of the perfect linear fitting. So then you can really extrapolate the total energy. Believe me that this energy is almost exact energy for this, let's say, model system. So we have 30 electrons in 108 orbitals, nearly exact values. Of course, so far I have talked about the Hamiltonian wave function. Okay, the final piece of information I want to talk to you is that the property. So in the Dirac picture, like relativistic formalism, we have only two types of physical properties, let's say, represented by either diagonal operator or off-diagonal operator. So this part basically corresponds to the electric field. There you have a scalar potential, and this off-diagonal operator represents a magnetic field characterized by vector potential. And in this, for the first part, basically you have the electronic excitation. Having this, we formulated the very first 4-component relativistic time-dependent functional theory. The thing on the so far. So I think the more challenge is this part. This odd operator, the off-diagonal operator. So let me show you one example. This is a nuclear magnetic shielding, okay, NMR shielding. So Dirac equation, Dirac is linear with respect to the vector potential. So if you formulate the NMR shielding, so you have the first order operator and the first order wave function. According to the convention, that this term is called a paramagnetic term. Paramagnetic, because the wave function will polarize, right? They polarize. So if you apply this equation, okay, Dirac equation to the NMR shielding of the helium atom. You know, helium one is square, it's helium atom. So you get a single number. It's called a parallel magnetic term. But if you run certain equation, again, for NMR shielding of a helium atom, you again get a single number, but there the single number is the diamagnetic term. So that's a dream case of a picture change. So in the non-relativistic theory, you have both diamagnetic and paramagnetic terms. But in the relativistic case, based on the Dirac operator, you have a single term, paramagnetic term. You have no diamagnetic term. Okay, and this is puzzling people for many, many years. Actually, the first person who tried to capture the missing diamagnetism was somehow I forget his name. Anyway, he tried this from already 1962, before I was born. Actually, before I was born. But it wasn't, the formulation was not successful until 2007, because all of the previous formulations, they did get two values, but only in an approximate manner, or the formulation suffered from singularities. Only the theory was formulated properly only in 1927 by our group. Okay. Oh, Ramsey, yes, Ramsey. So now again, I show you a particular example to convince you, right? And this is a calculated shielding of the halides, fluorine, chlorine, bromine, and iodine, compared to experimental value. That means the horizontal line is experimental value. Okay, the deviation from experimental value. So you can say this is non-relativistic calculations and very close to experimental value. But if we do relativistic calculations, and this is zero order regular approximation, and this is exact for theory. So we do more and more relativistic calculations, and we become worse and worse. This is a really funny situation. Okay, so the best theory deviate worst from experiment. So now, probably most people would say that your theory is probably rubbish. Okay, actually the opposite is true. I want to tell you, opposite is true. So NMR shielding actually is indeed observable, but it cannot be measured precisely in experiment. So instead, experimental people, as first measure nuclear spin rotation constant. This is microwave spectroscopy, which can be measured very precisely. And Ramsey in 1950 invented a mapping relation between this nuclear spin rotation and NMR shielding. So it basically means that you do experiment measurement on nuclear spin rotation, they map it to NMR shielding. Okay. In short, relativistic measurements are mapped to a non-relative value because this is a mapping. It holds only in non-relative limit. So basically, that's ample is ample, orange is orange. Okay, they are different. However, you can see this is identity. Okay, this is identity. So if we let the difference between ample and orange, as between the NMR shielding and the nuclear spin rotation constant, if this difference is very simple and very stable quantity, which you can calculate easily. Okay, then of course you can get the measurement, and plus this differential value, you would get another measurement. Okay, based on this philosophy, we established what we call relativistic mapping between nuclear spin rotation and the NMR shielding. You see, this correction term is really a relativistic correction. When the speed of light, c, goes to infinite, then this term disappears, of course. Then this mapping will become the same as the Ramsey's non-relative mapping. So now you can see that why the relativistic results are so bad compared to experimental results, simply because the so-called experimental results actually are mapped by a non-relativistic relationship. So if you use this relativistic mapping, what happens? And this is a relativistic mapped things. Okay, this is the original scholar experiment 30. So in this case, for iodine, the errors nearly 1300 ppm. Okay, and so nowadays we can really establish new experimental shielding scale according to our relativistic mapping just mentioned. Okay. So to summarize what I have told you that we just about 10 or 15 minutes, I explained the Hamiltonian, wave function, and the properties, these three components of the quantum mechanical equation. Basically, to summarize, we have designed an exact two-component theory, which is a seamless bridge between the Schrödinger equation and the Dirac equation. So we also have an effective QED theory, which is a seamless bridge between the Dirac equation and the Feynman QED. Okay, so I think we have reached the stage that to treat correlation, relativity, and QED on equal footing, such that we really can predict experiment. So, at least in my opinion, I mean, fundamental issues on the Hamiltonian wave function properties are very astute. Practical solutions have been found. So the big picture for relativistic molecular quantum mechanics has been established. But I'm not complaining that the theory has come to the end. Instead, it opened up a new era of relativistic quantum mechanics. So this is the ongoing things. So certainly we are trying to look at quantum electrodynamics effect in many electron systems, relativistic effect in many electron systems, in particular material science, solid states, things like that. And many body design, many body theory for especially for strongly correlated materials. So we are looking at the electronically solid states and non-adiabatic dynamics, which I have no time to talk about today. We also developed a relativistic energy theory, and at the moment we are working on the developing a new theory for solid state AMR. So in the end, I want to acknowledge my collaborators as my